Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is ACI 318 2019 Concrete Building Design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They're both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So I will quickly go over the content that we will be covering over the next hour today. I do want to begin with the new RFEM 6 features available for the ACI 318 concrete design. So we previously held a webinar on ACI design a couple years ago, so we've certainly have added new features since then. And then we'll move on to our example structure that you see over on the right-hand side. So we'll quickly go over the model and loading review. We'll talk about the building model add-on and how we can integrate these building-specific features such as diaphragms, but also shear walls and deep beams will be a big topic today, and how we can further design these with the concrete design add-on. And of course, with both the analysis and design, we'll take a look at the detailed results. So for those of you not familiar with our program and the add-on concept, I do want to quickly explain that for structure design related to concrete. So RFEM 6 is the base program. This allows us to fully model the structure. We can integrate with BIM software. We have access to all the materials and the cross sections in the library. And this is also valid for hybrid structures as well. We can load it and then we can get a full static analysis. If we want to take this a step further to design the columns, the beams, or the surfaces, we do need the concrete design add-on that will go ahead and carry out the design according to the ACI or the CSA or other international standards. We then have the building model add-on. So RFEM is a general FEA program, but this building model add-on will release these building specific features that now gives us the ability to define stories as well as shear walls and deep beams. And finally, there are many other add-ons that will be relevant, but for today, I just do want to mention a couple others that will be used in our example for dynamic analysis. And this includes the modal analysis add-on and the response spectrum analysis add-on to generate those seismic forces. Now, we won't be going into detail on these add-ons today, but we certainly have previous recorded webinars for both the ASCE 7 and the NBC that will go further in depth on this topic. Turning now to the new ACI 318 features that have been implemented since our last webinar. We now have the ability to carry out the punching shear design check. So this is for column to slab and wall end to slab intersections. Now, the current design check will only flag the user if two-way shear reinforcement is required. There currently is no input option for that two-way shear reinforcement, but we do plan to add that in the near future. We also have added additional Chapter 18 seismic design checks. Now, currently this is reinforcement detailing checks only, but again, we'll continue to expand on this in the near future, such as strong column, weak beam. Our section is a standalone program, and this allows us to calculate the cross-section properties of custom sections. For example, we can import in a DXF file. We might typically use this program for something like aluminum or cold form steel sections, but it also can be used for massive cross-sections such as concrete. So if you don't find your particular cross-section in the RFEM library, you can utilize our section. You can even place a reinforcement in this cross-section profile. It can be integrated further in the global RFEM model where we can carry out the design checks. Now, currently only member bending design checks are carried out. And again, we'll continue to add on additional design checks in the future. And finally, we have the building model add-on that releases these building specific features. And today we'll be focusing on shear wall design and deep beam design. So on the next slide here, let us talk a little bit more about the shear wall design that we will see in today's example. So this does require the building model add-on integration in addition to the concrete design add-on. Essentially, we draw these shear walls with 2D surfaces within RFEM. Well, when we define it as a shear wall, what's happening underneath the hood is that a result beam is going to be created. And a result beam just simply sums up the internal forces across this 2D surface and presents it as a beam type manner. Well, we also can input in the reinforcement under the shear wall dialog box. We have added this new cross ties input. Again, we'll see in our example today. As far as the design checks, we will refer to chapter 11 for the in-plane design checks, as well as out of plane, in particular, section 11.5. We'll carry out additional Chapter 11 detailing requirements such as spacing, minimum reinforcement, and as mentioned, we also have these Chapter 18 seismic detailing requirements where we'll go ahead and check the spacing and minimum reinforcement requirements here as well. Now, deep beam design follows very similar to the shear wall workflow in the fact that we do need the building model add-on integration. Very similar, this is also defined as a 2D surface. We create this result beam underneath the hood, but maybe instead of a vertical result beam for our shear wall, we have a horizontal result beam here to sum up all of the internal forces so that we can easily design this. The reinforcement input options are also available under the deep beam dialog box, and we have added the new diagonal coupling reinforcement input. As far as the design checks, we will refer to Chapter 9 for deep beam shear strength and detailing design checks, and we can also consider those Chapter 18 seismic shear strength and detailing requirements for coupling beams. So with that said, we will now turn to our example within RFEM. So when we begin a new model, we are presented here with the base data dialog box. Well, under the second tab are all of the various add-ons that we have available. So essentially, you're creating a custom software package that's specific for your design needs. Now, for today's example, I do want to begin by enabling the concrete design add-on, and then we also talked a little bit about those dynamic analysis add-ons that we'll utilize in our example here. Under the third tab for standards, we can generate the load combinations automatically according to the ASCE 7. You'll notice here the latest 2022 standard is implemented. We'll also take advantage of our automatic wind load generators as well as snow load generators. So we can set the standard here under the second option also to the ASCE 7. The concrete design is set to ACI 318, the 2019 standard, but you can see here the alternative standards that we have offered, including the CSA. And finally, dynamic analysis for the response spectrum analysis will be carried out according to ASCE 7. So now that we have this information set, you'll notice here that I have went ahead and modeled our concrete structure for today. So let's do a quick overview. We'll begin with the materials. So everything is defined here with 5,000 PSI concrete that was just implemented or pulled in from our material library here. Now, specific to concrete, we do have this second tab available to us under time-dependent properties of concrete, where we can further specify the creep and shrinkage behavior of this material. Now, this will come into play a little bit later on for those time-dependent deflections. If we do specify creep and shrinkage, we will refer to the ACI 435 for that consideration. For today, I'm not going to take advantage of anything related to the creep or shrinkage input. So we will now move on to the cross sections. You'll notice here that the columns are defined as 20-inch by 20-inch square sections. And then we have various beams here that are supporting the slabs and spanning in between the columns. Well, if I zoom in here and I double click on one of these members, I want to point out that the member type is not set to beam. So a beam is any standard column or beam element, but rather this is set to a rib. And when we specify this under this second tab, rib, we can actually define here the effective width on the left and right hand side of this beam element. So then we further have the ability to integrate the internal forces loads from the slab element itself from the static analysis, and then we can design it as a T-beam within the concrete design add-on. Now, for this rib element, we're at the edge of a slab, so we only have effective width defined here over on the left-hand side. But this is unique to rib elements rather, again, than a standard beam element. We also have the thicknesses defined here. So the thicknesses are assigned to the surfaces. For our shear walls, we have 10-inch thick concrete defined, and then for our slab elements, these are also 10-inch 5,000 PSI concrete. Down at the base of the structure, we have nodal supports at the columns that are rigid, and then we also have a fully rigid support at the base of our surfaces here that are defined as a line support. So we'll now move on to a loading overview. So going into the load cases and combinations dialog box, you'll notice under the load cases that I have defined here dead, live, snow, and wind. So these are our static load cases that once we have these defined here within this dialog box, we would actually need to apply the loads graphically to the structure. So we'll go ahead and back out here and take a look within our drop down at the dead load case. Now, self-weight is automatically considered underneath the hood internally for all of the elements, but I have added an additional surface load here of 50 pounds per square foot. Now, we are not confined to applying a surface load, as you can see up here with this option in our toolbar, to the entire surface itself. Rather, we also have these options right next to it called free loads. So for example, a new free rectangular load could be applied to just a certain portion of the surface rather than the entire surface as a whole. We also have the live load case here, same concept. The magnitude for the surface load was increased to 100 pounds per square foot. Then we have our snow load here at our roof level. And for this, I took advantage of the load wizards that you'll find over here in our dialog box. And under the load wizards, if you remember, we set this to the ACI 7 so that we can automatically generate the snow and wind loads. So if I go into this dialog box here, you'll notice that we just specified the geometry, we input in the parameters specific to the ACI 7, and ultimately the program is going to calculate these snow loads for us. Now, very similar, we have our wind load generator. So if I toggle here to my wind load case, we see this applied lateral load. And I'll go into the wind load dialog box here. Again, we input in the geometry points, the type of roof. We'll input in the parameters specific to the ASCE 7, and then the program can generate all of the wind load cases from case 1 and case 3 from the ASCE 7. For this simple example, I am just generating the minimum wind loads in both directions, so that's why you can see everything else is unchecked here. So for our first minimum wind load, we can see this applied area load laterally here in the global Y direction. If I'm interested, I can always right click to display separately, which is going to show me the loads applied to the structure based on the tributary areas. Now, if I'd prefer, I can turn this back off if I would like a cleaner area load display instead. And then similarly, we have wind load in the other direction with that applied area load. So going back to our load cases and combinations, I also have a couple of dynamic load cases here as well. Again, I'm not going into detail with this. This is covered in those previous webinars you can find on both our website and YouTube channel, but we do have a modal analysis load case where we're going to carry out the eigenvalue analysis to determine the natural frequencies, vibrations, mode shapes of the structure. We can import in here a mass combination for this calculation. And then we also have our response spectrum analysis load case. So we're going to refer to the ASCE 7 here to generate these seismic loads in the orthogonal X and Y directions. And ultimately, once we have all of these load cases set, we need to combine them into the load combinations. So under the design situations here, you can see that the program is automatically going to group together these load combinations in what we call a design situation. So we have our first two design situations here in orange that are going to include our factored load combinations from the ASCE 7s, 1 through 5. And then this second factored design situation is going to include all of our seismic loads. So 6 and 7, again, directly from the ASCE 7, we can click on this little info button here to see that information pulled directly from the standard. Now, we further have a couple design situations here for our unfactored loads. So we have the ASD load combinations 1 through 7, and then we also have 8 through 10 that will include those seismic forces. Now, these design situations are ultimately needed within the concrete design add-on, and we'll see this later on exactly how we assign the limit states to these different design situations. But for now, just think of these design situations, again, grouping together the load combinations. If we're interested, we can go ahead and click on the load combinations tab, and we see the load combinations listed out here individually. Our factored load combinations in orange belonging to that first design situation. We have our unfactored load combinations here belonging to the third design situation. And we do also have enabled here the result combination. So it's not possible to combine the seismic forces with the results of the other static load cases. So what I'm talking about is combining dead live snow with seismic. Therefore, we have to combine these results linearly in what we call a result combination. This is different than a load combination that is automatically going to be carried out according to a second order analysis considering P delta effects. Again, this is covered in that response spectrum analysis webinar, but ultimately these result combinations also belong to those design situations. So one more thing I want to touch on is that you'll notice that for the load cases, I have a structure modification set here, and this is really important for concrete design. If we go in and take a look at this definition, I have enabled both members and surfaces because these are the two elements that we have in our model today. And then I get two additional tabs up here up at the top. Well, within my first definition type here for members, what we have the ability to do is to directly select here the ACI 318. And this is going to refer to table 66311A to apply those I crack factors to our member elements within the model. We would want to select whether this is a column or a beam, and we can see the relevant stiffness modification factors given here. So once we have this definition, then we can graphically select all of the column elements within the model that this stiffness reduction should be applied to. Same exact concept here for our beam elements. And in a very similar manner, we also have the surfaces tab here that I created my first definition by simply selecting the ACI from this dropdown, and then I would choose whether it's walls uncracked, walls cracked, flat plates, or flat slabs. This refers directly to the ACI for those I crack factors, and then we can graphically select the surfaces that this stiffness reduction should apply to. So we could go ahead and apply this to all of our load cases. It's also possible here under our design situations, especially these factor design situations, that we go in here to the combination wizard options and we activate this structure modification here as well. So by doing it within the design situation, you'll see here that the load combinations automatically include those I crack factor stiffness reductions as well. So now that we have covered the loading and the structure, it's now time to input in the reinforcement that's specific to the concrete design add-on that we have already enabled within the base data dialog box. So before we begin, what you'll notice here is that we do have the concrete design option available within our dropdown of our table. So when we select this, there is this option here called global settings. Now, by default, the strength and serviceability design checks will always be carried out. But if we are wanting to further carry out those seismic detailing checks, we would want to go in here and turn this on because by default, this is typically not enabled. So we'll go ahead and do that for today. Okay, so we want to talk about the reinforcement input for a column. And if I double click on this column here, you'll notice that the design property checkbox is turned on. So this is telling the program that not only are we interested in carrying out the static analysis within the base program, but I also want to utilize that concrete design add-on to input in the reinforcement. Now, when I turn this off, you'll notice all of these tabs here disappear, and this is simply telling the program that we're only interested in the analysis. So we certainly could carry out the reinforcement input here within this single column, but I do want to talk about the benefit of what we call member representatives. And currently I have this turned off graphically within the model, so I'll go ahead and turn that on. But you'll notice that we have a lot of color-coded dots here for each one of these members. Well, this is because the program has grouped together identical members in what we call member representatives. So members that have identical cross sections, materials, lengths, and possibly even for concrete, the same reinforcement input will all be grouped together here. Now, the benefit is that if I take a look at the member representative number 1 here, you'll notice that this has grouped together all of my columns. So we see this highlighted in the background. Well, I have these exact same tabs here to input in the reinforcement as I do the individual columns. The benefit is that if I define the reinforcement here within the member representative, it's applied to all columns at once. If I need to go in and make a change, I do it within the member representative. Again, it's going to affect all the columns defined here. So we will go ahead and input in these various tabs, and I'll go through these in detail. The concrete effective length. So if we are carrying out a first order analysis and utilizing the moment magnification method, we would want to go ahead and input in an effective length. However, if we are designing to second order analysis and considering P delta effects, which we are within our load combinations today, we don't really need to do anything within this particular tab. So we'll go ahead and design according to second order analysis. Now the concrete cover should be input. This is left here at 1.5 inches, which is the default. Now I went ahead and input in the shear and longitudinal reinforcement for these members, so we'll just go ahead and give a quick overview. So the shear reinforcement is set at number 4s at 9-inch spacing on center. So we can see that spaced out evenly along the member here. Now it's entirely possible to create different zones for both our shear and our longitudinal reinforcement with this option in the lower left-hand corner. And then we can modify here the span location. So for example, if we wanted maybe closer spaced shear ties at the ends of the member versus the center, we could create a couple different zones here. The longitudinal reinforcement, you'll notice here that I have selected the option from our dropdown here as uniformly surrounding for the longitudinal bars. And I have defined 20 number 6 bars, so the program will go ahead and place these around the cross section as shown. Now we do have additional options here to define a development length if we would like. You can see that within the dropdown box here, where we can see the development length shown graphically. We can modify that development length itself in terms of feet. For today's example, I'll go ahead and leave all of the development lengths off, but that is where you would want to input in that information. Now, the design configurations, I'm only going to go through this tab once because it's the exact same application for all elements that we are designing. We have here these strength configurations to begin. So if I go into the default setting here, you'll notice that we have 4 different tabs depending on which element we're designing, whether it's a member or a surface or even punching shear. These are going to be all of the various options specific to the strength design checks according to ACI. So whether we're turning options on or off or we're modifying them, this is all again specific to the strength design. Now we did put in here the code references, so we're trying to clarify with you, exactly which settings you are modifying. You can refer directly to the ACI standard. Now, it is also possible here to create different configuration settings for different elements. Currently, this is assigned to all of our surfaces or members or punching shear, but you can create multiple definitions in the lower left-hand corner and assign to different elements. We also have the serviceability configurations here. Again, this is going to be specific to the serviceability design check. So for example, we can calculate the crack width. For surfaces, we have minimum reinforcement due to shrinkage and temperature. We also can check deflections. So whether that is simply supported or cantilever beams or columns, this also can be carried out for surfaces. And then if you remember, we talked about a little bit the time dependent deflection. So I had mentioned that under the material properties, when we input in creep and shrinkage for that material in more detail, we probably want to toggle this to refer to the ACI 435. So this is certainly a far more complex approach here within the serviceability design checks for that long-term deflection. Now, alternatively, when we leave this as default with the factor according to the ACI table 242413, we're simply going to apply some type of factor to the immediate deflection based on the duration of the load. So much more simplified approach. Okay, and finally we have the seismic configuration. So we'll go in here and you'll notice that for the seismic detailing checks, we can select for our members whether the seismic design category is one of the options from this dropdown. We also have the frame type here that is set to ordinary, intermediate, or special moment frame. And again, this is applicable to members and to surfaces for those additional detailing design checks. And finally, we have the design supports and deflection. So if I input nothing within this tab, the program is simply going to assume that this member is supported at both ends, and it will refer to the limiting deflection ratio for simply supported members. In contrast, if we have a cantilever, we probably want to assign a design support at the left or right end so that the relevant deflection limit is referred to. Now, I am just going to leave this as simply supported for our column elements, but we'll see in just a minute how we can set this differently for our rib members. So once this information is done, we want to move on to the reinforcement input for our 4 rib members over here on the right-hand side. So very similar to the columns, these are all grouped together in a member representative as well. So if we take a look just to quickly review this information, again, because it's a rib member, we are going to include the effective width here of the slab for the member design. And we run through these various tabs. Concrete cover is set to 1.5. The shear reinforcement is number 4, set at 6 inches. Again, we could set different zones if we would like. The longitudinal reinforcement. So this is going to be a little bit more detailed than what we saw with the columns. You'll notice that I have 3 number 6s set to symmetrical. So this is going to place, again, 3 number 6s up at the top and up at the bottom that are currently highlighted. Well, we also have an additional 3 number 6 bars defined here at the bottom with what we call the rebar type line. So this line option allows me to place a line of reinforcement, and I can specify the different offset either left or right or top or bottom with this input option. And finally, we have 8 number 6s that are defined in that surface effective width itself. So this was also defined with the line option. I modified the offset here, such as 8 inches, so that we can input in this longitudinal reinforcement within the slab element. So pretty simplified for today because we'd probably want to create different zones with different longitudinal reinforcement, but this is just a little bit of an overview for this simple example. And finally, the design supports. So what I would like to do with the beam element is maybe we want to reduce the shear force for our design check a distance of D away from the support face. Well, the only way to do this is to input in a design support. So you'll notice that I created a definition type here for a new support type, and the type must be set to concrete. we would set the support width, which I've set it to 20 inches to reflect the column that it's connected to. We would define here whether it's an inner support or not. In this condition, it's not an inner support. We also can define here if the support should be active for deflection design in the strong and weak axis. For clarification, I just went ahead and activated this in the strong axis direction. So once we create that support, we can select that same definition type here at the member end, and then we actually see the support shown graphically here in this dialog box. So this is how we can consider that reduction of the shear force. Okay, so now that this information is input for our beams and columns, what would typically be shown if I go to my second tab here under the navigator and I turn this into wireframe view, is we can actually view the reinforcement that we have input graphically in the global 3D model. So again, this is only specific to the elements here that I have defined so far. If you feel like that's a little overwhelming, you can always turn that off, of course. Now, to talk about the surface reinforcement, I'm not going to go through this. This was covered in a previous webinar, but it's the exact same concept where we can activate the design properties, we can input in the surface reinforcement, and similarly for punching shear checks, what we would want to do is to choose one of these nodes where it's framing into that reinforced slab. We double click on it, and very similarly, we have a checkbox here for punching design and an additional tab here that refers to the strength configurations for those punching design checks. So again, we won't be doing either one of those for today's example, but I just did want to mention that. So now it is time to move on to the building model add-on. So for this, I want to right click here to activate the base data dialog box, and under the add-ons, we will go ahead and turn on the building model add-on. And I click OK. So at first glance, nothing changes graphically here. The only thing that we now have access to in our navigator over on the left is a new folder called the building model. So we can now define our building stories in this general FEA program. So I'll go ahead and double click on this dialog box. And the program will automatically assume that we want to create our first story, and it detects the height of that first level. Well, we will continue to create the additional stories above it with the option here in the lower left-hand corner for a total of 4 different floors. Now, once we have created the different stories, you'll see here that for each one of our floors, we now have the ability to assign a diaphragm to this particular floor or to all of the floors, including rigid, semi-rigid, and load transfer only. So let us go back to the PowerPoint because I do want to discuss the building model add-on concept in more detail, as well as these different diaphragm options. So as mentioned, RFEM 6 is a general FEA program. We are not restricted to only building analysis and design. Rather, we can model tanks, silos, fabric tensile structures, maybe an FEA of a steel connection. Really anything is possible. But this building model add-on is releasing these building specific features in this general FEA program, such as the ability to define stories. Now we also have the option, which we'll see in just a minute, to define shear walls and deep beams. The added benefit of the building model add-on is that once we run the static analysis and even the dynamic analysis, we will get additional results available in table format for results by stories. So for example, if we're looking at a response spectrum analysis, we can actually view the story shear or the base shear in table format. For static or dynamic analysis, we can also view the shear wall forces in table format. We can export that out to Microsoft Excel quickly. If we have a rigid diaphragm, we'll be able to view in the table the center of rigidity as well as graphically where that center of rigidity occurs. So many more options, again, specific to buildings will be released. Now, as mentioned, we have now these various diaphragm types available. So we recently released semi-rigid diaphragms. So now we have all 3 options available to you, including rigid, semi-rigid, and what we call load transfer only, otherwise known as a flexible diaphragm. So when we choose to not assign a diaphragm within the building model add-on, or we choose the load transfer only, otherwise known as the flexible diaphragm, it should be known that really we're not going to see anything unique about the calculation. We're going to run a 3D calculation, including gravity and lateral loads. All elements are considered for all load combinations. However, when we choose a rigid or a semi-rigid diaphragm, not only are we going to carry out this 3D global calculation, but we're also going to extract each individual floor to run a separate 2D local calculation. So let us go to this next slide to explain this in a little bit more detail. Now, again, this is specific to rigid and semi-rigid diaphragm options only, where we are going to run these two separate calculations. And as I go through this, just keep in mind that we will see this in the results in our example today, so hopefully that will make more sense once we can see it applied. But the first 3D calculation, what we call the Wall's global 3D calculation, we are going to run through all load combinations. And this includes both gravity and lateral loads. The difference here, though, is that the floor in plane stiffness is going to depend on the diaphragm type. And I'm going to talk about the stiffnesses on the next slide of all the different options. But for the floor out of plane stiffness, this is going to be set to 0. So this is what you can expect with this 3D calculation. Then we're going to run an additional local 2D calculation. So what we do here is we extract each individual floor or diaphragm and all the surfaces that are included in that in the horizontal direction, as well as those rib elements. And we run a separate submodel calculation underneath the hood. Now, instead of the columns and walls framing up underneath this floor, we replace those with nodal and line supports. Now, it's important to understand here for this 2D calculation, though, that for both the in-plane and out-of-plane stiffness of this floor, we're going to set this to the actual stiffness, meaning we refer to the material, we refer to the thickness, we calculate the actual stiffness. So all in all, you can think of this 2D calculation really is looking at the gravity loads only, because in the lateral directions we're supported here with nodal and line supports, but we're also going to use the true stiffness properties that you have set with that surface element. So on the next slide, I thought it would be worthwhile to create this table to summarize the different diaphragm stiffnesses depending on the type that you have set for both the 3D and the 2D calculation. So you can certainly refer back to this table if you're integrating these diaphragm options, if you're wanting to know what type of stiffness is used where. So over on the left, we have the different diaphragm types, including rigid, semi-rigid, the load transfer only, otherwise known as a flexible, or if you have no diaphragm set. Now, the first couple columns here is going to be related to that global 3D calculation. The rigid diaphragm is going to use a no stiffness in the out of plane direction, but in the in plane direction, we set this to something infinitely high, a very, very high stiffness. In turn, for this semi-rigid diaphragm, again, out-of-plane stiffness is set to 0, but the in-plane stiffness is going to be the actual stiffness. So we're going to look at the materials, the thicknesses, and we're going to use the true stiffness properties in the in-plane direction for that 3D calculation. Then we also have the load transfer only, otherwise known as the flexible diaphragm. And for both out of plane and in plane, the stiffness is set to 0. And this is the entire intent of a flexible diaphragm. It doesn't add stiffness to the global 3D model. Rather, we use it to distribute loads only to the elements that it's attached to. And finally, we have here no diaphragm defined, in which case the out of plane and in plane stiffnesses will be set to actual. You can think of this as just a general FEA calculation. Whatever you have input in for that surface will be used for the global 3D calculation, no modified stiffnesses. Now, we also have the couple columns here at the end for the local 2D calculation. So in case we have defined a rigid or semi-rigid diaphragm, you can see here that the actual stiffness will always be used for both out of plane and in plane. Now for the load transfer or no diaphragm, remember we're not running a separate 2D calculation, so this is not applicable within this table. So we'll go back to our example today, and for all 4 of my floors, I'm going to define here a semi-rigid diaphragm. Now remember, for rigid or semi-rigid diaphragms, when we carry out that separate 2D calculation, we're replacing the walls and the columns underneath it with line and nodal supports. Well, rather than having those line and nodal supports set to fully fixed or fully released, the program can actually calculate the true stiffness of those elements framing up underneath it, and we can create an elastic support condition here with a spring stiffness set. So that's what I'm going to go ahead and use today. I want the program to refer to the true stiffness of those elements framing up underneath it. Okay, so once we have set this information, what you will notice here is that if I double click on one of my floor elements, the stiffness type is now set to floor slab semi-rigid diaphragm. I can't modify this because this is defined directly within the building model add-on. Now, in addition to the building stories that have been defined here, we now have the ability to create our first shear wall definitions. So before we do, I'm going to activate what we call the surface cells, and I just had turned them on graphically, and I'll go ahead and turn those back on. Surface cells are automatically turned on when we enable the building model add-on. And you can see here that it creates these surface cells at various portions of the structure on the surface elements themselves. Well, I'm going to turn this into an elevation view here, and I'll go ahead and highlight only my front shear wall. So here we have our 4 shear walls displayed graphically here, and you'll notice that those surface cells for the shear walls at the 2nd, 3rd, and 4th level are shown. And this is really helpful because this will help us define what is a shear wall on the left and right hand side versus what's a deep beam that's spanning in between these openings. Now, for this first shear wall, you'll notice that I don't have those surface cells. So anytime that you have a shear wall with an opening, what we need to do in order to generate these surface cells is to actually create a line element that spans from the opening to the edge of the surface. Now, we certainly can do this manually with a new line option up here in our toolbar and just graphically drawing that line. But I'd like to show you a quick trick here. It's in the program. With our drawing tools down at the bottom, we have this option to extend the line graphically. So something that you might find similar in AutoCAD. When I choose this option and I hold down the Alt key on my keyboard, what will happen here is that the program will automatically extend this line when I click on it, the upper left and right hand sides, without affecting the opening. And I'm going to do so here at the bottom right and at the bottom left. And now you can see that those line elements are automatically created again without affecting that opening. And the surface cells were automatically detected when we do this. So in case you have a shear wall with openings, you certainly want to take this workflow. So now we can define here our first shear wall by right-clicking within our building model folder. And we create our first shear wall definition. And we want to select here the surfaces or the surface cells. So I will graphically select all of my surface cells on the left-hand side of this opening to define one continuous shear wall on the left-hand side. So once this is done, I'm going to create a new definition type here. I'm going to do the same thing on the right-hand side of the openings. And we have one more shear wall definition. And for this one, I'm going to cancel out the visibility and I'll go back to a rendered view because I want to create my third shear wall over here on the left-hand side. Now notice this one doesn't have any openings. Therefore, we can just directly select the surface itself without having to worry about the surface cells. So once we have input in the shear wall definitions, We can hold down our shift key to select all of them because I'm going to input in the same options here for all 3 shear walls at once. Now, the first option here to generate the results section. Remember, I talked about how that result beam is created underneath the hood. Then we can present the internal forces that are summed up over these surfaces in table format. So that's just what we're enabling here for the static and dynamic analysis, just to present that in table format. Now, very similar to our columns and our rib elements, we want to turn on the design properties because we'd like to design these in the concrete design add-on. And then we have the additional tabs up here at the top. So the concrete cover is going to be set at 1 inch for our shear walls. I'm actually going to jump here to the longitudinal reinforcement first, and I'm going to select here the option uniformly surrounding. And with this option, I want to go ahead and place the reinforcement at the bent corners here of my stirrup, and then the number of bars is going to be set to 22 number 7s, and I select number 7 bars from my drop-down box here. So then the program just places these longitudinal bars all the way around the shear wall. We're kind of looking at it in a plan view here. Now, the only modification that I want to make is to shear wall number 3. This certainly has a much longer width to it than the first couple shear walls, so we'll go ahead and increase the longitudinal reinforcement to 40 number 7s, and we see graphically that adjust here. So now going back to the input for all 3 shear walls, we'll go back to the shear reinforcement. So with the shear reinforcement, I am going to select here number 5s from my drop down, and I'm going to adjust the spacing to, let's say, every 5 inches, so 0.417 feet. And this is a new option that we have added within the shear walls, is to go ahead and generate what we call the cross ties when I activate this checkbox. So now we see those cross ties enabled across all of the longitudinal bars here. Now, if you perhaps do not want to consider a cross tie at any one of these locations, you can just graphically click on the longitudinal bar here over in our preview, and that cross tie will be deleted. If you want to go ahead and add it back in, you just click on the longitudinal bar again, and you'll see that cross tie considered. Now, lastly, we have the design support. So very similar to what we saw with our member elements, we can also add design supports where it's framing into the slabs or the floors along the height of our shear wall. So for the start and end of the shear wall, I'm going to create a new design support of the type concrete. The support width is going to be set to 10 inches because this is how thick my slab is that's framing in the transverse directions. For this one, it will not be an inner support. I click OK, and then I can select this new definition within my dropdown, and we actually can zoom in here and see that design support shown graphically at the start and end of the shear wall. Now for my interior support, we can go ahead and create a new definition type. Again, very similar, 10 inches in width, but this time it will be an inner support. And we can go ahead and select this from our drop-down box here for all of the interior support options. Now you can also hit F8 on your keyboard to copy the cell from above into the current cell. But now we see those support conditions modeled along the height of the shear wall, again representing those slabs kind of framing in at those transverse locations. All right, so now that we are done with our shear wall input, let us talk about deep beams. So this is really going to be a very similar workflow. We're going to begin here by right-clicking to create a new deep beam. And the program will ask us which surfaces or surface cells we want to consider. So I'm going to zoom in here and choose the 2 surface cells that are spanning between the openings of my first and second floor. I'm going to create my second deep beam that will go ahead and span between the openings of the second and third floor. And finally, we are going to create here our third deep beam that spans between those upper floor openings. And I'm going to highlight all three of these to generate the results sections and also to turn on the design properties with the coupling reinforcement that is going to be specific to deep beam input. The concrete cover, will go ahead and modify this to 1 inch. And then we have the shear reinforcement. So I'm going to specify here number 5, similar to our shear walls at 0.417 foot spacing. We further have our longitudinal reinforcement. So for this one, I am going to select here from my dropdown, uniformly surrounding. And we're going to go ahead and place those rebar at the bent corners here of the stirrup with this checkbox. I'm going to select 30 number 6 bars. So the program will go ahead and place those evenly around the perimeter of this deep beam. And finally, we have the coupling reinforcement. So again, this is new, specific to the deep beam design. So you can see here that the first initial input is going to be the transverse reinforcement. So as I click on it, it's highlighted here just to kind of bundle these diagonal bars together. The default here is number 3 is at 1 foot on spacing. We'll go ahead and leave this as default. Then we also have the diagonal reinforcement itself that we can kind of view here, or we can zoom into the cross-section view. So this is going to be 3 number 6 bars set at both the top and the bottom. Now, additionally, we can set an anchorage or development length on either side of this reinforcement. So if we wanted to go ahead and do that, we would select the anchorage type straight. And we could also modify here the length to maybe 1 foot. You'll notice that we do see the input or the preview update here down at the bottom. We'll go ahead and set this development length to straight on the left side here. And the input is going to be 1 foot as well. Okay, so that will be all of the input here for this diagonal reinforcement. The final thing to do would be the design supports, but in this case, we really just want to consider it supported at both ends, really nothing to do further here. So we'll go ahead and click OK because we are now done with the reinforcement input for both our deep beams and our shear walls. Now, if we drop down to the concrete design add-on within table format, we have here the input data. And as mentioned, here are those design situations. So what I'd like to do is to take that first design situation, those factor load combinations that are grouped together, and set the limit state to the strength design LRFD. But then we also have the factor load combinations that include those seismic forces in the second design situation. So therefore, we want to choose the seismic design limit state from our dropdown. So we'll carry out not only the strength design for these load combinations, but also those additional seismic detailing checks that we talked about from chapter 18. We have here 2 design situations for our unfactored load combinations. These are both going to be set to serviceability design. Now, under the objects to design, you can see by default, the program just selects all objects within the model, but if we don't have reinforcement input for all of these objects, of course, it wouldn't be possible to design them. So we'll go ahead and leave the design of the shear wall and deep beams active, but for my members, I'm actually graphically going to select here only these frames over on the right-hand side that I have input in the reinforcement directly. So once we're done graphically selecting these, we click OK, and we're now ready to run our calculation. So we would normally go to calculate, calculate all. It does take a few minutes to run. So in this case, I am going to jump to an already saved model where this calculation has already taken place. So what we would see once we are done within the concrete design add-on is our results available to us in this dropdown where we can view the design ratios on members or shear walls or deep beams. So if we jump to the design ratios by member, you'll notice here that currently, as I'm clicking within this table, we are looking at this top column here. So we can zoom in and you'll see all of the strength, serviceability, reinforcement limits, and detailing checks that are carried out for every single member here. So we can continue to scroll down through this table and see those relevant checks. Now, for these specific design checks, we can always activate here what we call the design check details. And the design check details is going to show us in detail all of the calculations, the formulas, the variables, and ultimately how this design ratio was calculated. We also see here the design equations and references from the ACI standard, so we can refer to that directly within the code. So again, trying to be transparent in where this information comes from so that you can understand how this design ratio is calculated. Now for our columns, we can also activate here the interaction diagram. So now we get an additional tab up here at the top where we can view this 3D interaction diagram either graphically or in table format. We see exactly where we land within this interaction diagram. So this is certainly something that is user-friendly in terms of adding to our printout report or just understanding for that column interaction diagram, again, the results presented here. The same concept for our rib members. So notice as I graphically select one of these rib members, the table will go ahead and jump to that relevant member here. All of the design checks are shown here within table format. The design check details are available if we'd like to take a look at the references, code equations, and things as such as that. Now jumping to the design ratios of shear walls. So if we zoom out here, you'll notice that we're currently looking at our first shear wall. And again, all of those same design checks. However, we're carrying out the additional checks according to Chapter 11. We'll also see here some of those seismic detailing checks included. Again, similar to the member design, we can activate here the design check details to see exactly how this design ratio was calculated with the reference formulas here. Same thing for the design of the deep beams, of course, that we have designed. Now, everything is shown in table format, but it's also possible to show this graphically as well. So for example, if I kind of jump here to a wireframe view and we're looking at this deep beam that's spanning in between the two openings, well, we can turn on the design check ratios here for our deep beams, maybe not necessarily the overall ratio envelope, but rather for each strength limit design check, I can go ahead and turn that on graphically. And you'll notice that we can actually overlay these different design checks of this deep beam graphically as well, depending on which design check that we are displaying. In addition to the design checks, what you'll see here is the ability to display the reinforcement. So we'll go ahead and turn on the reinforcement display for shear walls, and I'll go ahead and zoom out here. Well, for my shear wall, I can display graphically the required longitudinal reinforcement. So this is the reinforcement that's required from the static analysis. I can overlay this on the provided longitudinal reinforcement. So ultimately, we hope that the provided reinforcement is greater than the required reinforcement. And if not, we can further display here what we call the not covered reinforcement. So again, in addition to all of the table output, a lot of graphical options here under the concrete design add-on. Now, the very last thing I want to do is to actually back up to the static analysis. So we were currently just looking at the design results within the concrete design add-on, but we can easily toggle here to the static analysis and choose one of our load combinations. So for example, I'll choose load combination number 6, which is dead plus snow plus wind. So we'll go ahead and turn on the display here of our structure. And you'll notice that because I have defined that semi-rigid diaphragm, or if we had defined a rigid diaphragm, we have the additional settings up here under the static analysis results, including that 3D calculation. So again, we're calculating in a 3D environment, all elements are considered. We're running through all of these load combinations here, both gravity and lateral loads. We're just going to modify the diaphragm stiffness for this global calculation. In turn, we can toggle here to that local 2D calculation. So you'll notice that we're only going to see results here for the floor elements themselves because we're extracting each one of these floors in a separate submodel. We're placing those line and nodal supports, and then we're going to apply the actual stiffness of the surface element itself. And we run through, again, all of these load combinations. Now, what's nice is that I don't have to sit here and try and interpret the results between the 3D versus the 2D, but we have this third option available. And this is going to combine both the 3D and the 2D results by adding them together and presenting it here graphically as one result. So again, very powerful that we're not just looking at gravity versus lateral. This is everything combined together. And not only graphically can we view these results, such as member internal forces, surface internal forces, but also in table format as well. We'll see those results change depending on which option we have selected here. Okay, so we'll go back to the PowerPoint here just to conclude our presentation today. I do want to quickly talk about a few future developments specific to the ACI that we're currently working on. And this is somewhat of a list of development features that you can expect maybe in order of release. So as mentioned, we're working on that two-way punching shear reinforcement input. So currently the program's just flagging you if that reinforcement is required, but there's no way to input it. So we will release that option in the near future, including for stirrups and headed shear studs. In a similar manner, the shear wall boundary element reinforcement input. Again, we're running this design check for shear walls, but we're only going to flag you if that boundary element reinforcement is required. So we want to also add in an easy input option under the shear wall to input in that reinforcement. As mentioned, for those R section, those custom cross sections, we want to continue to allow additional design checks beyond bending. Additional seismic design checks. Currently, we're just doing seismic detailing within the concrete design add-on, so we'll continue to elaborate on additional seismic like strong column and weak beam. Nonlinear concrete design is currently in development. We previously had this in RFEM 5, but we're really improving this for RFEM 6, where we can account for the true crack cross-section properties for both members and surfaces, and then we can consider that modified cross-section in both the static analysis and the design. And finally, foundation design. So this is also in development. It's certainly possible to do full reinforcement design of a slab on grade or grade beams or other type of foundation type elements, but we're obviously going to be missing some of those foundation specific design checks like sliding, overturning, or maybe optimizing the foundation size depending on bearing pressure. So you can expect that release in the near future as well. So this presentation was recorded today and will be placed on our website under the webpage that you did register for the webinar. You'll also find access to the model that I used in today's presentation where you can download it. If you don't already own RFEM, feel free to download the free 90-day trial version that you will find on our website. This is full capability. It includes all add-ons, including the ones that you saw today, for a duration of 3 months. If you have any questions about today's presentation or any of our products, feel free to contact our Philadelphia office with the contact information shown here at the bottom of the screen. Our phone number is 267-702-2815, and our email is info-us@delubal.com. If you are interested in scheduling an online demo, or you'd like to just have a quick online meeting to discuss some of RFEM's capabilities or ask any questions, we'd be happy to set that up. So you can either scan this QR code, or in the PowerPoint, this is a direct link to our website where you can go ahead and coordinate with our sales team to set that up. Of course, you can also directly email or call us with that information shown at the bottom of the screen as well. So we will have many more upcoming webinars. We hold these approximately once per month. You can register at delubal.com under support and learning webinars. As most of you know, I will send out a reminder email about a week before these take place. So just keep an eye out for that where you can register directly. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that attendees are here for the full 60-minute duration in order to receive that PDH. Now, if you watched in a conference type setting or you watched with a colleague and you yourself did not register with your own name and your own email under the GoToWebinar registration and you're wanting PDH, you can go ahead and request that to the email shown here, info-us@deluwell.com. So again, if you were here for the full duration and you yourself did not register, go ahead and send us an email, let us know who you watched it with, and we'll go ahead and send you that PDH certificate in return. Now, the PDH certificates are not automatic after this webinar ends. They're usually sent within 1 to 2 days. So just keep an eye out for your email when we go ahead and send those out when those are ready. And with that said, I want to thank everyone for attending. And as always, we hope to see you at our next presentation. Thank you.